Welcome back to a little bit more of mathematics, statistics in particular, and even more particular, discrete random variables as we start chapter 5. So we'll start this off by something that, if it sounds complicated, relax, it's not. A random variable is just something whose number is determined by the outcome of a probability experiment. So the probability experiment might be something like rolling the dice or flipping a coin, or you name it. It could be any of those things. The outcome is what you see as a result of that experiment. So maybe you roll the die and it comes up a 4. Or you roll dice and it comes up a 7. The variable is the number that comes up. What you'll see is a capital X represents the random variable and a small x represents the actual value. But there's a fine line between those two. You might have to give it some thought. X is the overall guy, and this is what happens any particular time. So this time it might turn out a 7, next time it might turn out 10, 2, and so on. These values are actually the small x's. The overarching concept is the variable itself, the outcome. And there we have a total of what I just mentioned. X is the name of the variable, and small x is how it turns out when you do an experiment. Some things to remember. First of all, when you're looking at the individual probabilities, those probabilities are between 0 and 1. Inclusive. They could be 0, could be 1, anything in between. That's what individual probabilities. Now, if you take all of them for a particular type of experiment, add them up, that's what sigma means, add them all up, you get a 1. If you've got a frequency table or something like this and you add up all those probabilities, you'll probably get something very, very close to 1 if it isn't exactly 1. So here's the total. Individual probabilities, 0 to 1. Sum of the probabilities, a 1. Next, we're going to create a discrete probability distribution for x, and the x is the sum on the die. The small x is what comes up next time we throw them. So here are all the possible values for x, all the possible small x's. This capital X represents all this that we're doing. Represents, take 2 die and add up the 2 values. The small x means what happened this time when I rolled the die, a 7 in this case. Now, before we get any further, why are they called discrete random variables? They're called discrete because they come in sort of chunks. For example, with the dice, we've got 2 here. Your possible values are 2, 3, 4, all the way up to 11 and 12. Notice they come in chunks. You can go and number them, count them. What you notice is there's no such thing as a 2.3 when you roll a die. You can't have the 2 die giving you a sum of 2.3. It comes in discrete chunks like this. That's why they're discrete random variables. You don't have values between, say, the 2 and the 3. It's only the 2, only the 3, and not an interval. Now, back to the slide. You're rolling 2 dice with 36 possible rolls. We just saw that. Each gives a sum between 2 and 12. You're probably familiar with that. You can get the 2, you can get the 12. To get the probability distribution, we need to calculate the probability for each value. If we sneak back here and look at those, we can see that there's only one way that that 2 can come up. You're familiar with that, snake eyes. Because there's only one way, that number 1 goes on the top. The total number of ways it could come up are 36. There's your probability for getting a sum of 2. Next, to get 3, go back to that list again. There are a pair of ways to get a 3. So you have the 2 on the top. 36 is the total for rolling 2 dice. And there's your probability. And usually we do one of two things with the probability. Either we reduce it, in this case to 1 over 18, or we change it to a decimal. By the way, just a tip for you, in case you do that, and you do get the 1 over 18, and you're thinking to yourself, doggone, I wanted a decimal. Well, the trick is on some calculators, some of them you do the second function like shift, enter, and you'll get the decimal, or maybe control, enter, force it to a decimal. On a lot of the calculators, if you just put a decimal point on either one of these numbers, any of them at all in the calculation, it forces to decimal. Just a tip for you. If you keep doing this, we've already got it for 1, or 2, and 3. If you continue going, you get a complete probability distribution for the sum of 2 rolled die. You could take a look back at that list again, and you can see count them up for yourself. For example, the 6 coming up, for example. There are 5 ways you can get a 6. You could have a 1 and a 5, 5 and a 1, 2 and a 3, 3 and a 2, or you can get 3 and 3. Total of 5 out of 36 possible rolls. Check those for yourself. Make sure that there wasn't a mistake by whomever made the slide. So one more time, the properties of a probability distribution of any kind, not just the discrete, but all probabilities. Any individual probability is between 0 and 1. And if you add up all the ones you have, say in a probability distribution, you get a total of 1. Next, we have something called an expected value, and that is very simply the mean of the probability distribution. This also means that if you want to find the expected value, you can use your mean function in the calculator, because the expected value and the mean are calculated exactly the same way. You multiply every possible outcome times that outcome's probability, get all those products, and then add all those probabilities up. And you should get a 1, or something very close to it, indicating that all you were off was just by rounding error. And a rounding rule, round to 1 more decimal place. 1 more decimal place than what you've got in the values of the random variable. In this case with rolling 2 die, it's always whole numbers, so you'd round off to the nearest tenth. If you're talking about money, however, you immediately round the 2 decimal places unless you're keeping equal dollars. So here's an example with those rubber ducks that I think we've talked about before. You've got to stand there and someone yelling, hey, come and try to find try to get a stuffed animal. If you get for a $1 ticket, if you get one duck that has a star on it, you get a small stuffed animal. You have 2 chances. You pick one duck, they put it back in, and then you pick the other duck. If you get one with a star, you get a small stuffed animal. If you get 2 ducks with stars, then you get an extra large stuffed animal. The first one is a $5 one, the second one is a $15 one. Now, here are the parameters. This is what you're working with. There are 50 floating ducks in that display. 3 of them have stars. What's the expected value of the carnival game? So what you need to do are 2 things. First, list all possible results. And second, list each probability for each of these values. So, the chance of getting 2 ducks to get the extra large stuffed animal. Each time you pull out a duck or select a duck, you have 3 starred ducks to choose from, and there are 50 of those altogether. So each probability is 50. Since they put the duck back in, then you're multiplying those 2 probabilities because you've got independent events. Multiply those 2 together, change it to a decimal. You can see why you probably would want a decimal value here, because 9 over 2,500 isn't something that you're very familiar with. So the second one, what's the chance of getting no stuffed animal at all? Well, there's 47 of those ducks that don't have stars on them. And since you're putting them back in, you've got independent duck selection. Multiply those 2 together. There's your probability of winning a stuffed animal of either kind. Also, remember, you paid $1 to play the game. So for this one, the outcome is you've lost $1. Winning the small stuffed animal. We've already done the 2 easy ones. Here's getting the large stuffed animal. Here's getting none at all. These plus getting a small stuffed animal have to add the 1. So if we take 1 and subtract the probabilities we already have, we've got the probability for a small stuffed animal. It's much easier than trying to do it directly. Good old complements. So here's our table. This is how you set one up. These are the results. What do you get from playing the game when you win? Well, if you win, you get a large stuffed animal worth 15, but you paid $1 to get in. So you actually gain $14 worth of value. On this one, this is where you don't get any stuffed animal at all. You just lose your $1, but you had some fun. And third, you actually got something worth $5, but you did pay to get in. So your net is $4 of value. Your probability for each one of those results, 0.36% of getting the large stuffed animal, a 0.8836 probability of not getting any stuffed animal at all, and 0.1128 is the probability of getting that small stuffed animal. Multiply these two together. Multiply, multiply, multiply. X if you want to, but hesitate to do that. Multiply these two together. $14 times 0.0036 gives you that. Over here, multiply, you get that, and that product. And at the end, once you've got those three products, add those together to get your expected value. Now, here's a good tip for you. How do you do that using your calculator? First of all, take the possible results, a $14 increase, a $1 decrease or loss, and a $4 increase in your value. Put those in list number 1. In list number 2, put these probabilities, 0.0036, and so on. Then do one variable statistics. Tell it you've got L1 and L2, and that's going to give you the expected value, which is written like this, which you'll see in the calculator like that. It's that easy, really. So the result is, when you do that, when you see X bar in your calculator, it's going to give you a negative 0.38. That means if you played this a lot of times, you would on average lose 38 cents per game that you played. That's expected value. Now how about some practical value for this? We're trying to decide between two different investment opportunities. Perhaps two stocks, and you've got potential earnings, and you've got their respective probabilities. Which plan should Peyton choose? You've got plan A, and you've got plan B. Which one do you pick? Here is a table showing the possible earnings and the probability for each one. So for the first one, you would earn $1,200 10% of the time. For plan A, you would earn $950 20% of the time. $130 40% of the time. Now, the bad part is, if you chose plan A, you're going to lose $575 10% of the time. You're going to lose $1,400 20% of the time. So, to find the expected value for plan A, you take each one of those earnings and multiply it times its probability, each one, and then add up the results. For plan B, we'll do the same thing. You can earn $1,500 in this one 30% of the time, $800 10%, and so on. Multiply this times this, 800 times 0.1, negative 100 times 0.2, and so on. Now this can be a little bit tricky By eyeballing it, you might come to a conclusion, but will you be right? Well, we have a way of figuring out whether we're right or not. So, and we're not going to do it by hand. I've shown you how to do that. Those are the expected values for the individual amounts. Using the TI-84, which I assume you're going to be doing, those are the values for Plan B, right there. L1 filled up, L2 filled up, go to one variable stats, and that's your expected value right there in front of you. So we're doing that for Plan A and Plan B. We can see with Plan B, you're going to, on average, you're going to earn $322. Plan A, only $24.50. Did you guess that way, or did you guess otherwise? So go with Plan B. Now, if you want the variance and standard deviation, do you have to go through all that? A big no. You're not going to do it that way. You're going to use the calculator. Really, why would you ever do this type of stuff when you can use the calculator? Or Excel, or whatever technology. If you want the variance, remember, this is about the rounding rule, but round them to 2 decimal places if it's money, and round it 1 more decimal place if it's not money. If you want to get the variance, just take the standard deviation that you got from your calculator, square it, and you'll get the variance. Standard deviation squared equals variance. That will give you an idea of how crazy some of these things can be. Which has more risk? There's where the standard deviation comes in. The more standard deviation, the bigger the risk. So just go back to your calculator. It should still be in there. Run one variable stats again, or you can go to variables under statistics. You can pick out your expected value and your standard deviation right there. For the first one, the expected value is $24.50, and you could go through all that. If you're not going to do it, don't even think about it. Just take the standard deviation and square it to get the variance. Do not pay attention to this. What I told you about how to find the expected value is the accepted way to do it. Don't bother with this. Get the standard deviation and square it. That is much easier, and you're much less likely to make a mistake. I have never found a use for sum of x, although there is a use if you just want all the x values added up. That's rare. This you can ignore as well, because you don't need to do this. If you were really curious, you would take this L3 when you're at the top here, and you could say L1 times L2, and that would give you the list 3. But as I said, please don't do that. That's silly. There you go. That's what they did. You don't need to do it. And we're finished with discrete probability distributions. See you again at 5.2. Bye for now.